I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
It's one small step for man, one giant leap for mankind.
I'm Wendell Mendel, a planetary scientist retired from NASA. I'm here today to talk to you about the environment on the lunar surface. Let's start with a question. Where are you? The answer I'm kind of looking for, which no one is going to give, is I'm in the universe. Now, that answer has probably no more information in it than the answer here, because everybody's in the universe. But the point I want to make is that when you live here on planet Earth, you really aren't too much aware of the universe unless you go out on a dark night and see the stars in the sky. And even then, you don't have a sense of the universe. The reason is that the Earth, with its atmosphere and its geomagnetic field, and even the sun with its magnetic field, put us in a cocoon that protects us from the universe. But once we get outside of all of that and get on some place like the surface of the moon, the universe is actually on our doorstep. So what property of the universe is important? First of all, the universe is cold. The cosmic background radiation that permeates the universe is at an effective temperature of 2.7 Kelvin, so everything radiates heat away to the universe. Now, on the moon, engineers have to make use of that property because normally when they design equipment to dissipate heat, such as habitats or motors or electrical circuits, on the Earth they have some way to carry that heat away using the atmosphere or maybe conduction into the ground. But on the moon, none of that really works. So the main mechanism for dumping heat is radiation to the universe. Radiation is a fairly inefficient way of transferring heat, so quite often engineers have to design quite large radiators in order to pump the heat into them and then radiate it away, and that presents sometimes a design problem for what they want to do. Coming in from the universe, the next part of the cosmos that affects people on the moon is the Milky Way galaxy. The galaxy generates highly charged energetic particles called galactic cosmic rays. They are accelerated by the magnetic fields in the galaxy, and they come in at high energies into our solar system. It's protons and electrons, but the really dangerous particles are highly ionized atomic nuclei. And if one of those comes into your body, it can destroy DNA and cause various havoc, molecular havoc inside your body that is very difficult to repair. So over time, exposure to the galactic cosmic ray flux predicts cancer, other sorts of damage to the blood-forming organs. So it's something that takes prolonged exposure to really be dangerous, but in general, people should be shielded from it, and the shielding is a bit of a problem. On the Earth, the atmosphere shields us from galactic cosmic rays with some help from the geomagnetic field and the solar wind. But on the moon, it strikes whatever is there, and so the traditional way to, say, protect a habitat module on the moon was to pile material on it from the moon. The material on the surface of the moon is called the regolith. I'll talk about that in a minute. And after you put a meter or so of regolith on top of a habitat, the elements from the galactic cosmic rays are indeed stopped. The problem is that the high energy particles can hit nuclei inside the shielding material and create radioactivities that decay and produced neutrons. And eventually there is a sea of neutrons which doesn't interact well with the shielding or with the habitat structure and comes in, and sometimes the neutrons are even more dangerous to human beings than the galactic cosmic rays. So right now the best ideas are that there is some kind of high density shielding with a hydrogenated material inside, like plastic or water or even human fecal matter, to keep people from being exposed to the neutrons. Moving in from the galaxy, the next environmental factor that we have to talk about is being in the solar system itself. The plasma that flows through the solar system is called the solar wind. It pushes back the interstellar medium and creates a bubble around the sun that we call the heliosphere. And so within the heliosphere, the main charged particles are those from the solar wind. The solar wind consists of two components. The low-speed solar wind is always flowing from the sun at a speed of about 400 kilometers per second. But occasionally there are eruptions out of coronal holes in the sun that create a high-speed solar wind that comes out at about a factor of 2 faster. The ions in the solar wind are overwhelmingly protons and electrons, but it also contains ionized nuclei, various other elements, and those gases impact the moon, and the grains on the lunar surface contain solar wind, and that is actually considered to some extent to be a resource because the moon is so deficient in volatiles that the solar wind gases in the upper surface can be mined in principle. The solar wind also interacts with the Earth's magnetic field, and the pressure from the solar wind distorts the Earth's magnetic field and causes it to stream out behind the Earth in the direction opposite from the sun, creating a configuration called the Magnetotail. And the moon, at 60 Earth radii from the sun, passes through the Magnetotail once a month. And so the charging environment on the surface of the moon, its interaction with the plasmas, changes with time, whether it's in or outside of the magnetic field. In addition to the normal solar wind, there are occasional explosions on the sun that can spew large fluxes of very high energy ions, primarily protons. These are called solar particle events, and the energy and the flux of particles is so high that it can be literally deadly to humans and can cause fatalities. A particularly dangerous solar particle event occurred between the Apollo 16 and the Apollo 17 missions, and had it occurred during either one of those missions, there may have been fatalities of the astronauts. This is a problem on the surface of the moon because when the solar particle events occur, astronauts have to take shelter. The problem is that there really aren't warnings for the solar particle events. The astronauts therefore have to have some sort of detector of the X-rays that precede the events, which take about 8 minutes to come from the sun. Then the solar particles themselves arrive in another 20 minutes or 30 minutes, and that is the time the astronauts have to take shelter. Unfortunately, solar particle events can last anywhere from hours to days, and so an astronaut just simply can't go and hide under some kind of overhang because the length of the event may be too long. The other property of the sun, which is important to the moon, of course, is sunshine. And the whole spectrum of the solar radiation hits the moon, whereas on the Earth, much of it is filtered out so that we only see the visible light in certain bands in the infrared. In particular, the ultraviolet is shielded when we live on the Earth. On the moon, the whole thing hits, and so this is not unusual in any kind of space travel, so engineers in general understand how to deal with the full electromagnetic radiation. But of course it obviously has effects on humans or equipment or materials that are exposed to it for long periods of time. The solar radiation is essentially that of a black body, and it follows the typical physics black body curve. The peak of the radiation is somewhere in the near infrared, but it has significant components in the visible and out into the thermal infrared. The unfiltered ultraviolet and X-ray radiation can be dangerous, and of course you shield against that, but this is a problem that's faced by any kind of spacecraft, any kind of operations in space, so engineers know how to deal with it. I hope everyone knows that a full moon occurs when the moon is on the opposite side of the Earth from the sun. So the same thing happens if you live on the moon and can see the Earth. The disk of the Earth in the sky, in other words, its moon, quote unquote, is about 4 times as large as the moon as seen from the Earth. The Earth is also brighter because it has a higher albedo. So the Earth light that shines on the moon during the lunar night can be quite bright and almost suitable for operations. In fact, on a very clear night when the moon is new, you can vaguely see the outline of the moon. It's called the old moon in the arms of the new. And the fact that you can see this dark part of the moon at all is due to the fact that the planet Earth is reflecting light onto the moon and then reflecting it back to where you can see it. The environment in the solar system consists of a lot of junk that's floating around the sun. The planets and their moons and the asteroid belt are pretty well behaved, but there's a lot of other stuff that can be floating around and come in at high velocities and impact the moon. And in fact, the moon is impacted quite frequently, but with submicroscopic dust particles. So these very tiny particles tend to erode the surface, form very small pits on the grains. But every so often, something of significant size comes in and throws up material which we call ejecta. The flux of meteoroids and larger bodies is about the same as we experience in geosynchronous orbit on the Earth. The Earth's atmosphere protects us from these most meteoroids up to a pretty good size. But as I said, they all hit the moon. The micrometeoroid impacts, which maybe cause only small pits, also have an effect on the surface grains of the moon, and sometimes can take some of the smaller grains and weld them into unusual glassy structures called agglutinates. Agglutinates are important to scientists who are studying the lunar soil, but that's beyond the scope of this talk. One of the things we're interested in is how often something large hits the moon, because that's when the crater is formed and ejecta is thrown out and could provide a hazard for habitats or people on the surface. In recent years, a telescope at the NASA Marshall Space Flight Center has monitored the moon when it's new and can see flashes of light from impacts. So we see maybe something like 100 flashes over 30 months. Problem is, no one knows how large the objects are that hit the moon and cause these flashes. Now, the risk to an astronaut or to a habitat from a direct hit is really quite small. It's the ejecta we worry about. At this point, I should mention that the surface of the moon, which has been subjected to impact for the history of the solar system, consists of broken pieces of rock, and we have a special term for it called regolith, which has an etymology that means broken rock. So every particle on the moon was once the piece of something larger. And the sizes go from submicroscopic, micron-sized particles all the way to huge boulders. And it's completely unsorted in the sense that there aren't layers of particles. There's just a jumble of everything. It's a quite unusual surface to work with, and so engineers have to become familiar with its properties in order to design equipment to operate on the surface or to move parts of the surface, like earth movers or drills, that sort of thing. The Earth is the only planet in the solar system that has a satellite whose size is significant compared to that of the parent planet. And in fact, in some ways, it's almost a double planet. Now, that makes the trajectories you calculate between the Earth and the Moon have some interesting properties which are beyond the scope of this talk. But the fact that we have a large moon has a dynamical effect on the movement of the Earth, particularly its spin rate and precessions. If you live on the Moon, the sun rises in the east and sets on the west, just like on the Earth. But the duration of a lunar day is very much longer. It's essentially 1 month. And whereas on Earth the day is 24 hours, and on Mars 24 hours and 40 minutes, on Moon a lunation, or a lunar day, is actually larger than 708 hours. So the sun moves quite slowly across the sky. If a person lives on the near side of the Moon, that part of the Moon that faces the Earth, that person sees the Earth in the sky, but it does not rise and set as the Moon does for us. It essentially stays in the same part of the sky and moves slightly around a fixed location. On the Earth, the spin axis is tilted with respect to the ecliptic, which is the path of the sun around the Earth. And that gives us an Arctic circle, so that if you live above a latitude of about 67 degrees, you have 6 months of darkness and 6 months of light. On the Moon, there's also an Arctic circle, but it's very tiny. The Moon's pole is only about 1.5 degrees off the vertical to the ecliptic, and so you have to be higher than 88.5 degrees latitude before you experience this 6 months of daylight and 6 months of night. The Moon is tidally locked to the Earth, meaning that it rotates exactly once after it completes one orbit. So one hemisphere of the Moon always faces the Earth, and we call that the near side. The other hemisphere of the Moon always faces away from the Earth, and we call that the far side. The orbit of the Moon is an ellipse, but the rotation is constant, while the orbital speed varies slightly at different portions of the ellipse. So from the Earth, the Moon shifts a little in the sky so that we can see a little bit on the far side depending where the Moon is in its orbit. And that shift are called optical librations. If you imagine a line that connects the center of the Earth to the center of the Moon, the point where that line hits the lunar surface is called the sub-Earth point. At that point, a person would see the Earth as directly overhead. The average position of the sub-Earth point is defined as the 0 point for selenographic coordinate system in analogy to the geographic coordinate system on the Earth. Some of the environmental effects that engineers must deal with come from the surface of the Moon but have their origin in outside effects. For example, the Moon reflects sunlight. The Moon is heated by the sun and gives off thermal emission. The Moon can be impacted by various objects, and ejecta can be a hazard to engineering operations. Neutrons are generated in the surface layer by the galactic cosmic rays hitting atoms in the surface layer and changing them to radioactive elements. And the surface itself can acquire electric charges through the interaction with the plasma environment of the solar wind. The Moon is in general a dark object, having an albedo of around 7%, although some areas are brighter than that, some areas are a little bit darker than that. If you look at a picture of the Moon, you see dark and you see light areas. The dark areas are basaltic lava flows that we called mare, the Latin word for seas. The highlands are the lighter objects, and these are the original surface of the moon before the great bombardments in the early history of the solar system. The reflectance of lunar soils, although they're really quite dark, tend to be slightly reddish, so the albedo or reflectance in the blue is slightly lower than the reflectance in the red and in the near infrared. The reflected light off the surface of the moon shows a surge at zero phase. And what this means is that when we see a full moon where the sun is right behind the earth and shining on the moon, all areas of the moon are at their brightest at this, what we call zero phase. And this reflective property was a puzzle for a number of years, but now we understand better what causes it. The upper millimeter or so of the lunar surface has a very porous structure that causes this very high retroreflection. I mean, retroreflection is a term like highway reflectors. When your headlights show on them, they tend to send the light right back to you. The moon is like that. If we are on the moon and looking down sun, that means the sun is behind our head and we're looking in the opposite direction, we see a loss of detail like you would see, say, on a ski slope where there's a whiteout and you can't make out what features are. This lunar photometric is odd, but it's very well documented and modeled and can be accounted for in engineering operations. The lunar surface is heated by the sun as it rises and sets, and is hottest when the sun is directly overhead. The temperature profile at any point on the moon is periodic. That is, as the sun rises and sets, it follows a particular curve that repeats itself over and over, day after day. When the surface temperature is periodic, the temperature measured at depth will also be periodic. But the shape of the curve with depth will change, and the amplitudes will become less. So that as you go down into the surface, the temperature variations around some sort of mean value get quite small rather quickly. And on the moon, the thermal inertia is quite low, and that means that as you go deeper into the surface, the thermal wave and the temperature wave that you see on the surface becomes muted so that the amplitudes vary only a little bit and as around a medium. So at a meter or so beneath the surface, a temperature probe does not even register the rising and the setting of the sun. The low thermal inertia of the lunar surface means that heat is inefficiently conducted into the interior. So the solar heat is collected at the upper surface, and that surface temperature quickly comes into radiation equilibrium with whatever the sun's input is. Of course, the sun's input is a maximum when it's directly overhead, and that's when the temperatures are the hottest. If there are slopes, the temperatures are the hottest when the sun is shining directly on the slope. So topography will exhibit a range of temperatures at any particular time of the lunar day. The lunar surface has large rocks sitting on it, and smaller rocks for that matter. Rocks, being more solid than the lunar surface, have a much higher thermal inertia. So heat is conducted into the interior of the rock more easily than is the case on the lunar soil. As a result, the rocks will remain cooler during the lunar day, and as the heat comes out of the rock during the lunar night, their surface will remain warmer than the surrounding soil. The galactic cosmic rays and the solar particle events strike the lunar surface with very high energy, and they can cause nuclear reactions with the atoms of the surface material of the moon. The interaction of the high-energy particles with the subsurface create temporary radioactive elements which decay and emit neutrons. These neutrons find their way out of the surface and can actually be detected from orbit, and sensors there can say what elements are in the subsurface from the way the neutrons are detected. The thermalized neutrons, the ones that moving at sort of slower velocities after they've bounced around a bit, can be absorbed by materials that contain a lot of hydrogen. This could be worked into shielding design, but it also can be a signature if there is any localized volatiles or water in the surface soil itself. And that's what the neutron sensors from orbit sometimes tell us, that certain places on the moon seem to have deposits of volatiles. Because the moon is immersed in the plasma of the solar wind and is bombarded by the solar UV radiation, the particles on the very surface of the moon can be charged. And the principal charging effect when the sun is shining is the photoelectric effect. And so photons from the sun knock electrons out of the grains, leaving them with a positive charge. And the amount of positive charge depends on how intense the sunlight is. So the charge is highest when the sun is directly overhead and falls off as the sun rises or sets. The net positive charge on the day side of the moon can be anywhere from plus 10 volts to about plus 18 volts. And as one moves toward the terminator, that is the dividing line between light and dark, the charge magnitude falls off. As one goes into the lunar night, the photoelectric effect, of course, is no longer present. And the plasma environment is changed because the solar wind has been blocked by the physical body of the moon. And the particles that go past the moon and the solar wind gradually fill in the void behind the moon, and the electrons are more efficient at moving into the void than are the protons. So the night side of the moon accumulates a somewhat negative charge of maybe about minus 10 volts. At the poles, the sun is always low on the horizon, and the topography can be quite complex. So this patchwork of light and dark shadow makes the calculation of the charge of the surface really quite difficult and almost impossible to do. When an object hits the lunar surface, particularly a large object, and forms a crater, the material that came out of the crater formation is thrown in the vicinity in all directions around the crater, and this is called ejecta. It can be quite high velocities and can be dangerous or damaging to people and materials. No one has ever actually seen the formation of a lunar crater, but scientists have mathematical models of what the process should be like, and they use the data from orbital photographs of large craters, like which maybe are hundreds of meters or more in size, and from some nuclear explosion craters on Earth to calculate what the ejecta patterns and ejecta velocities should be in the formation of a crater. The amount of ejecta depends on the size of the event. It can travel great distances, and in fact, in the case of some craters, such as the crater Tycho, we can see evidence that ejecta has traveled entirely around the moon and is on the back side. So the ejecta can be given high velocities. Fortunately, large events like the crater Tycho are really quite rare, but we have trouble quantitatively evaluating the risk to humans without more monitoring of the moon and the impacts thereon. When there's human activity on the moon, that can also disturb the surface. So a rocket landing will create an ejecta or surge just as if somewhat similar to an impact. And in fact, when a rocket lands, it can generate a temporary atmosphere from the rocket exhaust. During the Apollo landings, it was estimated that the entire mass of the lunar atmosphere increased by 30% just from the rocket exhausts of the landing spacecraft. Now I want to say a few words about dust. Dust is a colloquial term that's used by engineers to refer to the very small particles in the regolith. If you remember, the regolith has particles of all sizes, from boulders to microns, but the engineers are particularly concerned about the small particles and how mobile they might be and interfere with equipment or operations on the surface of the moon. On Earth, dust can be mobilized and carried into the air, so we're familiar with dust storms or a dusty atmosphere, and we know that in mines, dust can get into workers' lungs. The moon really has no sensible atmosphere or any wind, and any particles that are moved from the surface or dislodged from the surface travel in ballistic trajectories. The Apollo designers really had no operational experience on the lunar surface and did not make special efforts on the mitigation of the effects of small particles, beside just good engineering practice. There were no failures due to the dust on the lunar surface, but some evidence suggests that problems might have arisen if the operations were longer or if we were on the moon for longer periods of time where the exposure to dust was higher. Some engineers who were designing lunar equipment in modern times became concerned that the dust or the small particles on the lunar surface can be mobilized by the surface electric fields. That concern was triggered by various observations and anecdotal evidence that indicated some possible movement of dust, but there's really been no confirmed evidence that it's a major problem. We've had operational successes on dusty environments on Earth or on Mars, and they support the idea that good engineering practice and appropriate operations protocols can prevent failures from the presence of fine particles on the moon. The Apollo 17 astronauts in orbit made some observations of reflected light on the horizon at very high altitudes, which has been interpreted as a population of very small particles streaming from the moon, which supports the idea of electric fields being a problem. However, examinations by spacecraft orbiting the moon since that time have dismissed this as a serious problem. Everyone is familiar with the idea that the lunar gravity is 1/6 that of the Earth. However, low gravity is a design environment for engineers for which we have limited experience. The videos of astronauts moving on the surface show them loping as opposed to walking. That particular kind of movement might be the most efficient way to move on the surface. If that's so, and you're inside a habitat, how high should the ceilings be so that you don't bump your head? What should be the separation on stairs and staircases? And if you're designing things like distillation columns, which require gas to move through liquids, we don't know anything about how bubbles move in fluids in low gravity, although we can make theoretical calculations. So there's a number of practical considerations of operating on the moon that are hard to predict ahead of time, but we will learn through operational experience. The lunar gravitational field itself is kind of lumpy, and that's because the moon has some very large concentrations of dense mass not too far from the surface, and they cause perturbations in the gravitational field. In the Apollo program, this was not fully appreciated, and some satellites which were ejected from the Apollo spacecraft to orbit the moon and study the magnetic fields crashed after a couple of weeks, much to everyone's surprise. We now understand the lunar gravity field in great detail, particularly after the lunar Grail experiment. The Grail is a spacecraft that orbited the moon, and we now can take all that into account. The moon is generally regarded as a dead planet, meaning that nothing happens except for things that hit the moon and cause something to happen there. But there is some evidence from orbital photography and geological analysis that some things have happened in recent times. Now, for geologists, recent times can be the last 100 or 200 million years. And we're only concerned about what happened maybe last week. But even orbital spacecraft having detected bursts of certain gases, and seismometers have detected some kinds of vibrations, seismic activity. And there is a chance that some of these things really represent geological activity on the moon currently, although it's certainly not very large or impressive. The seismometers in place by the Apollo astronauts operated for 7 years on the lunar surface and recorded a series of events which are not understood very well. The magnitude of the seismicity, the vibration of the surface, is extremely small and actually in the nanometer range, which is, of course, totally insensible to human beings. The analysis over the many years of the type of seismic events came up with things which were called moonquakes, which means it's just things that are happening internal to the moon. The most common were called deep moonquakes. They occur very deep inside the moon and may be associated with just tidal forces between the Earth and the moon as it orbits the Earth. Then there are shallow moonquakes, which have the highest energies, and it's not clear what these are. Then there are just thousands and thousands of very tiny events which may just be thermal in nature, flexure due to heating of rocks. Of course, in addition to these endogenous events, there are impacts. The seismometers were able to detect the impact of rocket bodies that were crashed into the moon during the Apollo program. And of course, occasionally something must have hit the moon while the seismometers were operating, and they detected these things. And the largest natural impactor was estimated at 5 tons somewhere on the moon. And then, actually, most of the events are just unclassified. They don't have a clue as to what they mean. But once again, these are very small and don't present dangers in the sense of an earthquake to habitats or operations. The return to lunar samples from Apollo were dated by radioactive dating techniques, and the conclusion from that analysis is that the major volcanic events on the moon were over with about 2.5 billion years ago. But there are other ways to estimate the age of surface features based on counting craters and assuming you know something about how many craters fall over a certain period of time. Crater counting indicates that some surfaces may have been formed only a few 100 million years ago, which is short in geologic time. But for operations, the moon still can be treated as a dead and inactive planet. However, the alpha particle spectrometer on the Apollo's 15 and 16 missions detected traces of radon and polonium, both radioactive gases, emanating from certain parts of the moon, notably at the edges of the lunar seas of the Maria. On the surface of the moon, as part of the ALSAP instrument package, the Apollo suprathermal ion detector experiment saw bursts of gas that might be correlated with the seismic signals interpreted as impacts. At least one class of seismic waves are not well understood and may well be associated with tectonic activity. None of these observations represent a threat to human exploration, but they do suggest that our knowledge of the moon is somewhat incomplete. I really should say just a word about the lunar atmosphere, of which there is essentially none. The lunar atmosphere is really technically a surface-bounded exosphere. And what that term means is that the individual molecules are so spaced apart They don't even collide with one another and mostly collide only with the surface itself. The number density per unit volume is maybe 1,000th that of the International Space Station altitude at the Earth. So, and each Apollo landing temporarily increased the volume. Each Apollo landing temporarily increased the volume of the atmosphere by 30%. In this talk, we've discussed characteristics of the environment on the surface of the moon. We've done it for the benefit of people who might be designing equipment or planning operations, or even for people who will be working on the surface of the moon. Many of the unfamiliar characteristics of the lunar environment trace back to processes in our galaxy or on our sun, and these phenomena are unfamiliar to Earthlings because our geomagnetic field and our dense atmosphere provide us a cocoon to protect us from the bad stuff in the universe. Much of the exotic phenomena discussed might be familiar to aerospace engineers who design spacecraft and plan astronaut activities in orbit. Unlike the Earth, the moon has no weather, no geologic activity, and the state of the surface materials, particularly the regolith with no water and no weathering, may provide unexpected challenges to the operators there. But with experience, we'll make it work. And of course, we have to get it right the first time to have a second time. But remember, the laws of nature still apply on the moon, and the materials there are not inherently malicious.